Hey, Nerd Life. Jonathan here. Do you like physics? More specifically, astrophysics? Well, I certainly do. Recently, there's been quite a buzz about black holes. In fact, scientists managed to take a picture of one, Sagittarius A. But before we talk about black holes, let's talk about something possibly even more interesting: relativity. In physics class, you've probably heard the term inertia. Basically, it's the resistance to any force. You may also be familiar with this equation, F equals mg, and its counterpart, F equals mg m over r squared. Both equations can be combined to find any specific variable included. For example, mg equals gmm over r squared, where m represents the mass of an object, big M represents the mass of the Earth, g represents the gravitational constant, r represents the distance between the two objects, m again is the mass, and g is, well, g, which is what you're solving for. So if you cross out m and m, then we're left with g equals gm over r squared. So you could solve for g, or you could solve for any other variables using this, well, combination of equations. But most importantly, it relates mass with the strength of the gravitational force. Let's say you have a ping pong ball. Now, ping pong balls usually have a mass of about 2.7 grams. Now, converting this to kilograms by dimensional analysis, this gives us 0.0027 kilograms. Now, using the gravitational constant, having a value of 9.8 meters per second squared, you can plug it into this equation, F equals mg, and that gives us our gravitational force in newtons. So if I take out my calculator here, and I do this calculation, 0.0027 times 9.8, that gives us a force of 0.02646 newtons, and that's downward. Basically, what this says is if you have a ping pong ball on the Earth, it'll be pushed down with a force, or attracted with a force, of this. And a newton is basically a kilogram meters per second squared. And if you multiply this out, kilograms times this, then of course it turns out to be this, and that's what a newton is. But now let's say you have an even bigger ball, like a medicine ball, and let's say that it's 20 pounds. Now there's a basic conversion from pounds to newtons, and it's pretty standard here on Earth. Converting 20 pounds to newtons thus gives us our answer by dimensional analysis. So 20 pounds times 1 pound, 4.45 newtons, cross, and that gives us an answer, 20 times 4.45 equals 89 newtons, and that's downward. As we explained earlier, let's say we have a medicine ball here on Earth. It's getting attracted to Earth at this force. However, you must keep in mind that this conversion factor only works on Earth and other planets with an identical mass and radius of the Earth. Why do I say mass and radius? Well, according to this equation, it depends on the radius of a planet and the mass of a planet. So that's why it's the same on Earth as other planets with the same mass and radius. Now, when Einstein was working on his theories of relativity, he mentioned the principle of equivalence. Now, the principle of equivalence basically states that the inertial mass of something is identical to its gravitational mass. And what that means, basically, is that what we just calculated for the ping pong ball and the medicine ball. But this principle can also be stated in a more intuitive and thought-provoking manner. According to Physics for Scientists and Engineers by Giancoli, there is no experiment observers can perform to distinguish if an acceleration arises because of a gravitational force or because the reference frame is accelerating. Now, if you think about this, it makes perfect sense. Let's say you're in a spaceship and you drop a ball, and basically the spaceship is still in the atmosphere. It's really high up, but there's still a gravitational force. Of course, there's always a gravitational force. This one's just significant enough for a ball to fall to the ground. Now, if you drop a ball from your hand in a spaceship high in the atmosphere, this effect would be indistinguishable from the apple falling due to an upward acceleration of a ship itself. So basically, you drop it, oh, that's because of this gravitational acceleration. But it also could be if the ship was going up, then it would fall downwards. Now, this principle also applies to light and how it may be affected by gravity. Einstein predicted this in his general theory of relativity, a topic that I may discuss later in greater detail. If light can follow a curved path, then we infer that space itself is curved. Now, what do I mean by this? Well, here's our gravitational field. And if we curve this gravitational field, it'll be sucked inwards like this. Sort of like if you pull on a rubber sheet. And you've probably seen this diagram before. And here's this curvature of space. This natural curvature of space. So this is how space can be curved. As light follows a curved path, then space itself is curved. Well, this brings up the question, what can cause these really significant curves in the gravitational field? Well, a black hole, of course. A black hole is basically a dead star that is incredibly dense and massive. And when I mean massive, that means it has great mass, not that it's really big. If its gravitational field is unimaginably strong, not even light can escape its pull, which is why it's black. Also, there's a region in the black hole called the event horizon, and once you cross this, there's no coming back. Our local black hole around this area is known as Sagittarius A. We even have a picture of her. She's quite beautiful, actually. So that's what I have to say about basic gravity calculations, the principle of equivalence, and black holes. I'll see you all later, and my next video will involve this theory of relativity and the various complex calculations involved. As always, thanks for watching.